Occasionally, our solar system welcomes visitors from distant regions of the universe. One particular visitor, Oumuamua, is making a return appearance. We delve into the reasons behind its return and what implications it holds for our solar system. Join us as we explore the intriguing reappearance of Oumuamua and its trajectory toward our solar system. Is it an asteroid, a comet, or perhaps an alien spacecraft? Oumuamua, a mysterious asteroid stretching up to 400 meters in length, has perplexed astronomers for years. Dubbed by astronomers for its unusual characteristics, Oumuamua bears resemblance to an asteroid but exhibits behavior akin to a comet. Gravitational interactions often cause the dispersion of minor remnants such as comets and asteroids during the formation of planets around stars. Initially categorized as a comet upon its discovery, doubts arose among astronomers due to the absence of a prominent, billowy coma typically associated with comets when heated by the sun. Some scientists speculated that Oumuamua could be a rocky asteroid or possibly a novel type of interstellar object. Others argued that Oumuamua might be a planetesimal, a fragment of rock ejected from its original system due to gravitational forces. There is even a notion that it could be a zombie comet, or, as described in one publication, an enormous, incredibly porous conglomerate consisting of loosely bound dust grains left behind by a disintegrated comet as it approached the Sun. However, there is a particular reason why comets pique our interest. They serve as preservers of a snapshot capturing the early stages of our solar system's formation, resembling the protoplanetary disks we study today. Studying comets allows us to glimpse into the past and visualize the appearance of our solar system during its nascent phase. These interactions propel celestial pebbles from their planetary systems into interstellar space, where they embark on journeys lasting millions of years. Currently, the prevailing scientific consensus leans towards classifying Oumuamua as a comet, primarily due to its slightly faster than expected movement, which cannot be solely attributed to gravitational dragging from the Sun. The most plausible explanation suggests that the object, resembling a comet, is expelling material, creating jets that propel it forward. Observations indicate that it is 10 times more reflective than comets typically found in our solar system. This increased reflectivity could be due to the outgassing process, which has blown dust off its surface, revealing the sparkling ice beneath. The object's motion, driven by these jets, almost gives the impression of a spacecraft that originated from another star, swiftly passing through our system before propelling away. This intriguing concept has captured the attention of astronomers and researchers at the Search for Extraterrestrial Intelligence, SETI. They have been actively listening for any potential technological signals emitted by the object, not just once, but on 2 separate occasions. However, both campaigns yielded no response. Avi Loeb from the Harvard-Smithsonian Center for Astrophysics, along with co-author Shmuela Bayali, presented their own hypothesis. They suggested that Oumuamua could be a light sail, a thin, gossamer-like propulsion system that utilizes photons from the Sun, developed by an advanced extraterrestrial civilization. Their reasoning was based on the notion that outgassing would have altered the rotation period of the visitor, an impact that should have been noticeable but wasn't. Loeb speculated that Oumuamua might be a discarded piece of space debris that unintentionally entered our system, or it could be an exploratory vessel sent to investigate our region. While only a few scientists have supported Loeb's statement, he believes that dismissing the possibility of aliens outright disregards valuable theories that should be considered in a thorough investigation. But how did Oumuamua end up in our solar system? The space object was initially detected by the University of Hawaii's Pan-STARRS-1 telescope. Having circled the Sun, it was about to depart our solar system and was given the name Oumuamua, meaning messenger from afar arriving first. Astronomers worldwide utilized telescopes to observe this interstellar visitor for 4 months before it became too faint to be seen. Oumuamua, however, did not neatly fit into the established scenarios. While it shared similarities with asteroids, the object's acceleration during its journey indicated that more than just gravity was at play in its movement. The object exhibited a pushing effect similar to how comets are propelled when they approach the Sun. The evaporation of gas and dust by the Sun's heat generates this propulsive force. The force of the expelled material also slightly alters the trajectory of comets as they orbit the Sun, setting them apart from asteroids and planets. Oumuamua, however, did not resemble a typical comet. It lacked a tail or a coma, the gas and dust envelope that comets typically possess. This immediately sparked controversy among astronomers, and scientific interest in Oumuamua intensified as various models emerged to explain its acceleration. These models implied that the object possessed unusual chemical properties. Two scientists joined forces and collaborated on strategies to test their theories regarding the interstellar comet's acceleration. They proposed a hypothesis that Oumuamua was a water-rich comet traversing the interstellar medium, the space between stars. Over time, the reddish object was bombarded by radiation, causing hydrogen to form within the comet. Previous studies had shown that ice could transform into molecular hydrogen, suggesting that a comet's snowball-like structure could contain hydrogen bubbles within the ice. According to their theory, when the sun's heat warmed the body, the bubbles would expel gas in a fan-shaped spray. The water ice would then restructure into a more stable and compact form, allowing the trapped gas to escape. The duo argued that this could explain Oumuamua's behavior without resorting to exotic chemistry or physics. The propulsion of the small object was driven by hydrogen gas produced from the interstellar comet. Interestingly, the absence of a dusty coma around Oumuamua can also be explained by the same phenomenon. Even if there is dust within the ice matrix, it does not sublime along with the ice but simply rearranges as the ice changes, allowing hydrogen to escape without carrying the dust particles. This aligns with the expected behavior of interstellar comets, and observatories like the James Webb Space Telescope can aid astronomers in gaining a better understanding of comet formation in planetary systems beyond our own, as well as the composition of these exocomets, as stated by Bergner. In 2025, the Rubin Observatory in Chile, equipped with advanced technology, is set to open. Astronomers are hopeful that it will enable the discovery of several interstellar comets similar to Oumuamua each year. This would provide valuable insights into the characteristics of comets originating from other planetary systems. Interestingly, the comets and asteroids within our solar system have arguably taught us more about planet formation than the planets themselves. It is believed that studying interstellar comets can offer us greater knowledge about extrasolar planets compared to direct measurements of those planets. The Rubin Observatory's Legacy Survey of Space and Time (LSST) program, spanning a decade, will extensively survey the skies in the southern hemisphere. Had LSST been operational before Oumuamua's passage through the inner solar system, we would have detected it much earlier in its trajectory. Given its close proximity to Earth, we could have potentially sent a space mission to intercept and rendezvous with Oumuamua. However, there is still hope. As we discover more interstellar objects in the future, we will have the opportunity to launch dedicated space expeditions to study these objects. Some scientists are particularly eager to examine Oumuamua up close since that is the only way to gather more information about it. The prospect of catching up with Oumuamua is truly exciting. In fact, there are several mission proposals aimed at achieving exactly that goal. One example is Project Lyra, put forward by the Institute for Interstellar Studies, I4IS. This proposal explores the feasibility of using advanced propulsion technology to rendezvous with and study interstellar objects, ISOs. According to their recent research, if the mission concept were launched in 2028 and executed a sophisticated Jupiter-O berth maneuver, JOM, it could potentially catch up to Oumuamua in 26 years. The Initiative for Interstellar Studies, I4IS, initiated Project Lyra shortly after Oumuamua's discovery. The primary objective of this concept study was to assess the feasibility of a mission to Oumuamua using current or near-term technologies. Subsequently, the I4's team conducted studies on intercepting the ISO by employing nuclear thermal propulsion, NTP, and a laser sailcraft, similar to the Breakthrough Starshot project, a proposal for an interstellar mission aiming to reach Alpha Centauri within 20 years. Many previously proposed methods for reaching Oumuamua using near-term technologies rely on the concept of a solar oberth maneuver, SOM, which involves a solar diver approach. An excellent example of this approach is the work by Corin Baylor-Jones, a researcher at the Max Planck Institute for Astronomy. The SOM technique leverages the sun's radiation pressure to achieve a high velocity using a light sail. The essence of the solar Oberth maneuver lies in applying a boost when the spacecraft is moving fastest relative to the body it is orbiting, in this case, the Sun. The closer the spacecraft's orbit is to the Sun, the faster it will be. However, to benefit from the Oberth effect, the spacecraft must withstand the intense heat generated, requiring it to come as close to the Sun as possible. At the core of the SOM and other Oberth maneuvers is the gravity assist technique, which has been utilized for exploring the solar system since the early 1970s. This technique involves utilizing the gravitational force of three bodies: the spacecraft, a second body, typically a giant planet, that provides the assist, and the central body around which the spacecraft's trajectory is controlled. The solar Oberth maneuver, SOM, consists of three distinct velocity changes, also known as impulses, to propel the spacecraft out of the solar system. These impulses include increasing the spacecraft's distance from the Sun at aphelion, slowing down and approaching the Sun at perihelion, and obtaining an extra boost at the closest point to the Sun. During perihelion, the spacecraft reaches its highest speed. The term solar Oberth maneuver seems to have originated from Theodor Edelbaum's work in 1959, and it has since become a commonly used term. This maneuver is particularly fuel efficient for achieving high speeds when leaving the solar system, which is crucial for catching up with an interstellar object, ISO, after it has passed perihelion and is rapidly moving away from the Sun. As demonstrated by the Parker Solar Probe, getting closer to the Sun requires a robust heat shield capable of withstanding the extreme heat and radiation. The heat shield on Parker Solar Probe has a diameter of approximately 2.44 meters, 8 feet, and weighs around 72.5 kilograms, 160 pounds. While the size and weight of the heat shield for Project Lyra would likely differ, it is reasonable to assume that a solar heat shield would significantly increase the mass of the light sail. Considering Oumuamua is the closest interstellar object to us, a dedicated rendezvous mission would offer immense scientific benefits. By the middle of the century, humanity may get its first glimpse into the workings of distant star systems through a relatively affordable rendezvous expedition. Moreover, such a mission would finally provide answers to the many questions raised by Oumuamua during its historic flyby of Earth years ago. However, Oumuamua might not be the only interstellar visitor from outer solar space. In fact, another comet that recently made a remarkable swing around the Sun could potentially have originated from beyond our solar system. Ever since its discovery, astronomers have been puzzled by the origin of Comet 96P Machholz. This sun-grazing object, measuring 4 miles wide, exhibits a unique set of characteristics that suggest it originated from another star system. One notable feature is its highly inclined orbit, which brings it closer to the Sun than nearly any other comet. These distinctive traits, among others, led scientists to believe that 96P Machholz was redirected into our solar system due to an accidental collision with Jupiter during its intergalactic journey. Interestingly, the comet's encounters with Jupiter have obscured its true origins, raising the possibility that its peculiarities stem from an unconventional region within our own solar system or as part of a nearby celestial body that broke apart. Nevertheless, the comet continues to provide breathtaking images during its closest approaches to the Sun, known as perihelions, throughout its 5-year orbit. Since its inception in 1995, the Solar and Heliospheric Observatory, SOHO, a joint project by NASA and the European Space Agency, has been meticulously tracking 96P Machholz's perihelions. It was Donald Machholz, an amateur astronomer from California, who first spotted 96P Machholz using binoculars back in 1986. Recent investigations have unveiled that the object is remarkably low in common components like carbon and cyanogen, and it lacks the dusty atmosphere or coma typically observed around other comets in our solar system. Based on research and observations of 96P Machholz's perihelion, scientists propose that the comet might consist of a completely stripped-down nucleus with a primordial and possibly interstellar origin. However, even if we were to launch a mission to intercept the comet, it might not provide definitive answers about its past. Nonetheless, as we delve further into the mysteries surrounding this enigmatic comet, scientists are likely to discover numerous additional interstellar objects in the years to come. This follows the discovery of the first confirmed interstellar comet, 2I Borisov, and the identification of the first known meteors that likely originated from another star system before impacting Earth. However, the intriguing similarities observed between the nucleus of 96P Machholtz and Oumuamua may further support the argument for 96P Machholtz having an interstellar origin. This implies that the surface properties of the comet were acquired over millions of years through cosmic ray bombardment between star systems, rather than evolving within our own solar system. However, the mystery surrounding the genesis of 96P Machholtz may remain unsolved, partly due to the challenges associated with investigating this elusive object. Due to its tilted orbit, 96P Machholtz never comes close to Earth, and its lack of activity makes it challenging to study, except during its perihelion. Satellite telescopes like SOHO may provide some insights, but many mysteries surrounding the comet, including its origin, remain unknown. On August 30, 2019, Gennady Borisov, an amateur astronomer from Crimea, made a significant discovery at his observatory. Using a handmade telescope, he spotted a faint object moving against the backdrop of stars. He reported his discovery to the Minor Planet Center, which confirmed the identity of the comet and assigned it the provisional designation C 2019 Q4 Borisov. Further observations revealed that the comet had a hyperbolic orbit, indicating that it was not gravitationally bound to the Sun and originated from outside our solar system. Its eccentricity, which measures the deviation from a circular orbit, was recorded at 3.36, significantly higher than that of any known solar system comet. Additionally, it had a 44-degree inclination, representing the angle between its orbital plane and the ecliptic plane. On December 8, 2019, the comet reached its closest distance to the Sun, known as perihelion, at approximately 2 astronomical units, or 300 million kilometers. It made its closest approach to Earth on December 28, 2019, at a distance of about 1.8 astronomical units or 270 million kilometers. Currently, it is moving away from the Sun and will eventually depart our solar system for good. 2I Borisov displayed a coma, which is a hazy envelope of gas and dust surrounding the nucleus, as well as a tail consisting of material being pushed away by the solar wind and radiation pressure. The nucleus of 2I Borisov was estimated to be approximately 1 kilometer in diameter, similar to many comets within our solar system. Its peak brightness occurred in late November 2019, reaching a magnitude of about 15, which made it visible only through large telescopes. Spectroscopic analysis of the comet revealed a reddish surface, indicating the presence of organic compounds. Additionally, common cometary volatiles such as water, carbon monoxide, and cyanide were detected. However, notable differences were observed as well. For instance, 2I Borisov had a higher concentration of carbon monoxide compared to typical solar system comets, suggesting its formation took place in an extremely cold environment. The arrival of 2I Borisov provides a unique opportunity to study an object originating from another star system, offering valuable insights into its development and history. By comparing it to comets in our solar system, astronomers can gain a deeper understanding of the diversity and history of planetary systems within our galaxy. Furthermore, this comet contributes to our understanding of the origins of Oumuamua, the first interstellar visitor discovered in 2017, which exhibited more asteroid-like characteristics. As 2I Borisov gradually fades from view upon returning to interstellar space, it is unlikely that we will see it again unless we develop advanced tools for tracking or intercepting such objects. However, with improved surveys and sensors, our ability to detect intergalactic visitors may increase, leading to the discovery of more of these fascinating objects in the future.